Good day to all of you. Today we shall discuss on model question paper Set-2 of the subject Digital Design and Computer Organization with subject code BCS302. In that, question number 4a. Explain the working of 4-bit adders using 4 full adders. This is asked for 6 marks. So we have to discuss here how 4-bit adder works, which is implemented using 4 full adder. One full adder adds 3 bits. 4 such full adders using what 4-bit adder is implemented, its working we'll have to discuss. Solution. Let A and B the two 4-bit binary numbers. So first number A has 4 bits, namely A0, A1, A2, A3 are the 4 bits. In B, B0, B1, B2, B3 are the 4 bits. So we have to consider how A and B 4-bit binary numbers are added. So in paper when we write two numbers, A number is written here, B number is written here, both are being added. So here A0, B0, A1, B1, A2, B2, A3, B3. Apart from this, one more inputs we have C0, C1, C2, C3. C0 is the carry input to LSB stage, that is 0 stage here. In the next bit 1 stage, carry 1, that is C1, then C2, C3. They are the carry inputs, okay, that are generated by the addition of previous stage 3 bits. So when A0, B0 is added with the carry input to this 0 stage, that is C0. So there some bit in the 0 stage and carry bit what is generated by addition of these 3 is given as carry input to next stage, that is C1. Carry generated by A1, B1, C1 addition, that is C2, that is given to next stage. Some bit is written here, carry bit will be written here. So by when A2, B2, C2 are added, what carry is generated, that is given as carry input to next stage, that is called as C3. But for LSB stage or stage 0, the carry input that is taken as C0 and that is assumed here 0. And in 4th stage, what carry is generated, that is taken as C4 and that is also called as C out. When A and B are added, the whole answer is this C out bit, which is C4. Then in each stage what some bits are there, S3, S2, S1, S0. All these 5 bits form the answer of A plus B. That is addition of all these along with carries. So what answer is generated? There will be 5 bits. One is carry out bit or C4 bit, then S3, S2, S1, S0. Okay. Here when A0, B0, C0 are added, these are the 3 bits. The combinational circuit which can add 3 binary bits is full adder. So first full adder is taken for this. Another full adder taken that will add A1, B1, C1. Similarly, third full adder will add A2, B2, C2. Fourth full adder will add A3, B3, C3. So for addition of two 4-bit numbers, 4 full adders are taken. So this is the 4-bit adder block diagram. Okay. So 1, 2, 3, 4 full adders are shown. For the first full adder, C in, A0, B0 are the input. C in, A0, B0 are the inputs. Here C in is C0. Here C in is C0, that carry input to 0 stage. So this full adder, it will add all the 3 bits. It generates some bit and carry bit. So the carry generated in 0 stage goes as carry input to 1 stage, that is C1. So that is shown here. So second full adder will add A1, B1, C1. So A1, B1 are given here, C1 is coming. All the 3 are added. So second full adder generates some bit S1 and carry bit C2. So second full adder adds A1, B1, C1. It generates some bit S1 and carry bit C2. Third full adder adds A2, B2 and C2. It generates some bit S2 and carry bit C3. So third full adder adds A2, B2, C2, generates some bit S2 and gives carry C3 to next bit. So fourth bit adds A3, B3 and C3, generates some bit S3 and carry bit C4, which is also called as C out bit. Fourth full adder adds A3, B3, C3 and which generates some bit S3 and it gives out carry out bit that is C4. So this C4 that is here S3, S2, S1, S0 all together form the answer. So this is what is 4-bit adder and how using 4 full adders it is implemented and how carry from the first stage it is rippled through all the stages till last stage. To write, figure shows 4-bit adder using 4 full adders. One full adder can add 3 binary bits. Let A3, A2, A1, A0 and B3, B2, B1, B0 be the two 4-bit binary numbers A and B. When these are added to add A0, B0 and carry in bit that is C0 bit which is assumed to be 0, first full adder is taken. This gives some bit S0 and carry C1. Carry C1 is given as carry input to second full adder. It adds A1, B1 and C1. Carry generated by second full adder is C2. It is given as carry input to third full adder. This adds A2, B2, C2, generating some bit S2 and C3. Fourth full adder adds A3, B3 and C3. It generates some bit S3 and carry bit C4. C4 bit is also known as C out bit from 4-bit adder. Bits C4, S3, S2, S1, S0 form the answer or sum of A and B. Here carry ripples through different stages of full adders. So this is what is the explanation for 4-bit adder which is implemented using 4 full adders. Okay. Next we shall discuss question number 4b. Design a BCD to XS3 code converter. This is asked for 6 marks. BCD to XS3 code converter. Okay. Solution. BCD to XS3 code converter converts the given BCD number means binary coded decimal number to XS3 number. Both are binary numbers only. But BCD number is different, XS3 number is different. Okay. So how it is different? We shall see through the truth table. So this is what is the truth table for BCD to XS3 code converter. Okay. Here input BCD is shown. The output will be converted XS3 code. Right. So BCD means binary coded decimal. So in decimal 0 to 9 are the basic digits. So to represent them in binary minimum 4 bits are required. They are taken as A, B, C, D. So in A, B, C, D are the 4 input variables. So how decimal number is written in binary using 4 bits? 0, 0, 0, 0. How 1 is written in binary using 4 bits? 0, 0, 0, 1. Then 2 as 0, 0, 1, 0. 3 as 0, 0, 1, 1. 4 as 0, 1, 0, 0. 5 as 0, 1, 0, 1. 6 as 0, 1, 1, 0. 7 as 0, 1, 1, 1. 8 as 1, 0, 0, 0. 9 as 1, 0, 0, 1. Okay. Next, 10 to 15, they are taken as don't care conditions. So why we are talking about it? Here 4 input variables are there means how many combinations will be there? 16. 2 raised to 4 equal to 16 combinations. Starting from 0 to last one it should be 15. Okay. So this is 0, 1. This way till 15. 1, 1, 1 it should be. But 10 onwards we do not consider. 10, 11, 12, 13, 14, 15. They are treated as don't care conditions because decimal means it is 0 to 9 only. So binary coding of decimal is done for only base digits of decimal that is 0 to 9. So 10 to 15 they are considered as don't care conditions. Next, when input is in BCD, what circuit we design, it should give XS3 code as output. So when 0, 0, 0, that is 0 is coming on input side, that is binary coded decimal. So this decimal number is coded in binary, means it is represented in binary. So when this is the input, at the output XS3 code means 0 plus 3. So when 0 comes at the input side, 3 should come in binary. So in access to input by 3. So 1 should be 1 plus 3, 4 at the output. In binary it is 0, 1, 0, 0 is 4. When 1 in binary 0, 0, 0, 1 is coming, 4 should be at the output in binary 0, 1, 0, 0. When 2 is at the input, 2 plus 3, 5 should be at the output. How 2 will be at the input? In binary. How 5 should be at the output? In binary. So here 0, 0, 1, 0 at the input. Output we should get 0, 1, 0, 1. 3 means 0, 0, 1, 1 at the input. Output 0, 1, 1, 0 means 6. So 3 plus 3 is 6. So the output should be in access to the input by 3. That is access 3 code output. So XS3 code converter is the combinational circuit that converts the given BCD input to XS3 code. So 4 means 4 plus 3 equal to 7. So 0, 1, 0, 0, that is 4 in binary at the input. Then the output will be 0, 1, 1, 1, that is 7 at the output. 5 at the input means 0, 1, 0, 1. Then at the output 1, 0, 0, 0 means 8. So 5 plus 3 is 8. 6 at the input 0, 1, 1, 0 means at the output 1, 0, 0, 1, that is 6 plus 3 is 9. 7 at the input means 0, 1, 1, 1. Then 1, 0, 1, 0 at the output means 7 plus 3, 10. At the input 1, 0, 0, 0 means 8. 8 plus 3 will be 11. So hence at the output 1, 0, 1, 1. So 9 at the input means in binary 1, 0, 0, 1. So 9 plus 3, 12 should be at the output. Hence it will be 1, 1, 0, 0. So this is how we have written truth table for input BCD to output XS3 code. Okay. So next, how many outputs are here? W is one output, X is another output, Y is third output, Z is fourth output. By seeing each column, we'll have to write the K-map and fill it. One K-map for W output, another K-map for X output, third K-map for Y output, fourth K-map for Z output. 4 K-maps we'll have to draw. Okay. In that K-map, minterm 0 to 9 we will fill. 10 to 15 we will take as cross, means don't care conditions. And for these minterms, wherever W is 0, wherever 1 it is, we will fill, because we are going to realize the equation in SOP, sum of products form, only once we will fill. Logic 1 we will fill. Okay. So with this background, we shall go to K-maps. So from truth table, we can fill the K-maps. So K-maps section. So this is the K-map for W, and this is for X, and this is for Y, this is for Z. So ABCD binary bits in BCD, binary coded decimal, was expressed in terms of 4-bit ABCD, that is as 4 variables input. For 4 variables, 2 raised to 4, 16 squares K-map has to be drawn for each. So they are drawn here. Then W column, seeing to that in the truth table, 1 are filled. Next, wherever don't care conditions, means minterm 10 to 15 don't care conditions. So this is minterm 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these are the minterm places. So minterm 10, so 8, 9, this is 10, 11, 12, 13, 14, 15. They are all don't care conditions. So they are filled with cross mark. Then wherever in W column it was 1, that is filled here. So which mean term is this? 5, 6, 7, 8, 9. For these in W column in the truth table it was 1, that is filled. After filling we have to realize groups. So here a group of 16 is not possible. Then to cover these two 1, these don't care conditions are treated as logic 1. So don't care conditions must be treated as always as per the need of simplification. Because here we are going to write the equation in the form of SOP, we have to sum of products, we have to consider only ones, then and group ones, and then these cross marks or don't care conditions must be treated as logic 1. So 1, 1, 1, 1 and these two 1 all form one group. Okay, that is an octet. So with this octet these two 1 are covered. Next these 3 are remaining. Then with the help of these two 1 quad, with the help of these two another quad is formed. There are 3 groups. If you consider this octet, all the members are covered in these two rows 1, 1, 1, 0. This first one with respect to A is common, that is written here. All the 8 members of this octet are covered in 4 columns. So column wise 0, 0, 0, 1, 1, 1, 1, 0, nothing is common, leave it. Hence A is the term for this octet. Next, for this quad, 4 members are there. With this, these two 1s are covered. These cross mark are treated as 1. Okay, as per the need of simplification. These 4 members come in these two rows 0, 1, 1, 1. So second one with respect to B is common, so B is written. Then these 4 members, they are covered in these two columns 1, 1, 1, 0. This first one which belongs to C, that is common. So row wise B is common, column wise C is common. Hence BC is written for this group. Next, for last group, these 4 members, they are covered in these two rows 0, 1, 1, 1. So here second one which corresponds to B, that is common, hence B is written. These 4 members column wise, they are covered in these two columns 0, 1, 1, 1. Hence second one with respect to D, that is common, D is written. Hence BD is the term for this group. So W is equal to A plus BC plus BD. That is what is written here. So we have formed the simplified sum of products equation for W output referring to the truth table. Next, similarly for X output referring to X column in truth table, these are filled. Okay, so 10 to 15 cross mark is common for all. After filling, here considering ones, they have to be grouped. To cover these two, this one group is made, that is quad. To cover this with the help of this, these two and these two, another group, cross mark are treated as 1. Then this one is left, nowhere 16, 8 or 4 kind of group can be made, pair can be made. So this is paired with this cross mark, treating this cross mark or don't care condition as logic 1. So grouping is over because all the ones are covered. So next, for with respect to this group, right, 4 members, they are covered in these two rows. Here 0, 0, 1, 0, second 0 is common, that is B. So B dash, that is written here. Okay. Then again for the same group, they are covered in these two columns. So 0, 1, 1, 1, second one with respect to D, hence D. So B dash D is the term for this group. Then this red color quad, again members do come in these two rows 0, 0, 1, 0. This is second 0 with respect to B means B dash. For these two members, 4 members, these two and these two members of second group, here they are covered in this column and this column. 1, 1, 1, 0 means first one which is common with respect to C, that is written here, C. Hence B dash C is the term for this quad. Okay. Then for this pair, these two members are covered in these two rows 0, 1, 1, 1. Hence second one is common with respect to B. So B is written. Next, these two members, they are covered in this single column. 0 0 is common with respect to CD, hence C dash D dash. So X is equal to B dash C plus B dash D plus B C dash D dash, right? So similarly, Y expression. So another K map is drawn, and in that seeing to Y column in truth table, these ones are filled. This cross marks as it is from 10 to minter 15. Okay. Then to cover these two, this one quad is taken. To cover these two, another quad is taken. So all the ones are covered. We should not try to cover cross marks only once. Taking the help of cross mark we can do. So with respect to this group, here all the four members, they are covered in these four rows. Row wise nothing is common. Leave it. They come in same column, hence 0 0 which corresponds to CD, C dash D dash. It is written. For second group, all the four members, they come in all four rows. Row wise nothing is common. They come in this single column. 1 1 is common with respect to CD, hence CD. Hence Y expression is equal to CD plus C dash D dash. Similarly, Z expression, seeing to Z column in truth table, these logic ones are filled. Cross mark as it is or don't care conditions. Minterm 10 to minterm 15. So next, group of 16 cannot be made, but these 4 and these 4 can be treated as octet, because on this line if you take a fold, these 4 members fall on this. Again on this line you take a fold, these two come here. Then again on this line if you take a fold, all come in one square. Hence these 4 members and these 4 members form one group of octet. Okay. Then these 8 members are covered in 4 rows. Row wise nothing is common. These 8 members are covered in 2 columns, 0 0 1 0, that second 0 with respect to D, hence D dash. So Z is equal to D dash. Okay. So what we have done, truth table we prepared for BCD2 XS3 code converter. Then seeing to truth table, 4 outputs were there, 4 K maps we have drawn, and 4 simplified expressions are derived. Now seeing to these Boolean equations, logic diagram must be drawn. How to draw? BC means B ANDed with C, one AND gate. B ANDed with D, another AND gate. So here no gate, just input A. All must be ORed. That is the circuit for W. In this way, the circuit for X output, Y output, Z output must also be drawn. So the logic circuits for all the output forms one circuit for BCD to XS3 code converter. Okay. Now here the expressions obtained for W, X, Y, Z outputs are little bit manipulated algebraically for the purpose of using common gates for 2 or more outputs. The manipulation is as follows. Z equal to D dash, that expression is written as it is. But from K map what we have got, Y equal to CD plus C dash D dash. This is written as CD as it is. But using De Morgan's theorem, if you take C dash D dash, it is the complement of C plus D. So this is substituted with this. Next, X equal to B dash C plus B dash D plus B C dash D dash we had got from the K map. Here taking B dash common, into bracket C plus D can be written here. So these two are substituted with this, and this is written as it is. So if we see this, then again what is happening here? B dash into bracket C plus D is written. Here B in bracket C plus D dash. C plus D dash, how we have seen here, C dash D dash is equal to C plus D dash, that is taken here. Okay. So this is the complement of this, right? The same we have utilized here. W equal to A plus BC plus BD A is written as it is, B is taken common, then into bracket C plus D will be there. So what is C plus D here? One OR gate is taken. For that C and D are given as input. The output is ANDed with B. Okay. The output here it is connected to NOT gate and that is ANDed with B. The output here it is ANDed with B dash. So the output here connected to NOT gate, then ORed with C and D. This is how in terms of C plus D the circuit will be drawn. That's all. So the logic diagram that implements these expressions is as follows. So this is the logic diagram of BCD to XS3 code converter, which is drawn seeing to manipulated expressions, right? So W is equal to A plus B into C plus D. So C plus D. So this is a C and D. Plus D means logically OR. That C plus D is coming here and B is coming here. B ANDed with C plus D. That is what is this. Then that is ORed with A. So that is ORed with A. So this is W output. Similarly, X is equal to B dash into C plus D. Okay. So this B dash is coming here. Then C plus D. So C plus D means C ORed with D, that is coming here. Both should be ANDed. Both are ANDed. So what we have here, B dash into C plus D. Then the other one is B into bracket C plus D dash. So this C plus D was coming, that is complemented. C plus D dash is here. B is here. Both are ANDed. What we have here, B dash ANDed with C plus D. That is this. So both are ORed. So this is X. So Y is CD. So this is C and D. Both are ANDed, CD. This is C plus D. Then it is complemented, C plus D dash. That is this. It is coming here. CD is coming. Both are ORed. Okay. So this is Y. Z is D dash. So where is D? This is D input. Through NOT gate it is taken. Hence D dash is coming. That is what is Z is D dash. This is how BCD to XS3 code converter is designed and implemented. Designing means finding the logic equations and implementation means drawing the logic diagram, seeing to which components can be brought and in actual hardware they can be connected and implemented. Okay, so that completes 4B. Next we shall solve question number 4C. Demonstrate the working of SR latch and edge triggered D flip-flop. This is asked for 8 marks. So first we shall see to SR latch. So this is the logic diagram for SR latch using NOR gates. This is using NAND gates, right? Their function tables are written here. So SR latch when implemented using NOR gate here. So we can see here with in the diagram S and R are called as two inputs. S is for set input, R is for reset input. They are the names for those inputs. Q is the output. Another output is Q dash, which will be the complement of Q output. Okay. So here the condition is this latch will have two outputs Q and Q dash. At any time both cannot be same. They have to be different. If Q is 0, Q dash is 1. If Q is 1, Q dash will be 0. So this is the function table for this SR latch that describes the behavior of this. When both S and R inputs are 1, 0. Here logic 1, here 0. Then the output is 1, 0. Here logic 1, here 0. So then if 0, 0, if the input is changed to 0, 0, the output will continue to be same as previous 1, 0. That is called as no change. Next, if input is changed to 0, 1, if S is 0, R is 1, the output is 0 and Q dash is 1. So next again if you change the input to 0, 0, the output remains to be 0, 1 only. That is no change. So from this what we can make out, when both the inputs are 0, 0, there will not be any change in the output. It continues to be same as the previous state. So it was previous state only here. This was previous state only here. But we cannot give both S and R as 1 and 1, because then both the outputs try to be 0, 0, which is forbidden, right? So here S is called as set input. When S is 1, R is 0, output is set to 1. When S is 0, R equal to 1, the output is reset to 0. Reset means make the output 0. Set means make the output 1. So that is what was this. Next, NAND gate based SR latch, if you take here, when the inputs are 1, 0. So S is 1, R is 0. The output is just reverse. Q is 0, Q dash is 1. Here 1, 1 means the input conditions, the previous state only is continued, no change. If inputs are 0, 1, the output is 1, Q dash is 0. Next, if inputs are changed to 1, 1, the output remains same as previous, no change. Here set input is 0, it makes the output 1. Reset input is here, that is 1 here, that makes the output 0. S equal to 1 will reset the output. S equal to 0 will set the output. Resetting means making the output 0. Setting means making the output 1. Just the reverse of this. When inputs both are 0, 0, the outputs both try to be 1 and 1, which is forbidden state. So these two are SR latch in terms, one in terms of NOR gate, another in terms of NAND gate, and these are their function table, which in tabular form describe their behavior. Okay. So to write here, S means set input, R means reset input. S equal to 1, R equal to 0 will set the output Q to 1 in case of SR latch using NOR gates. But it will reset the output Q equal to 0 in case of SR latch with NAND gates. S equal to 1, R equal to 1 inputs are forbidden in case of SR latch with NOR gates, because both Q and Q dash outputs try to become 0, 0, which is forbidden. If Q equal to 1, Q dash should be 0 and vice versa. S equal to 0, R equal to 0 is forbidden in case of SR flip-flop with NAND gates, only because both Q and Q dash outputs try to become 1, 1, which again is prohibited. S equal to 0, R equal to 0 brings no change in the Q output. It continues to be same as previous state in case of NOR gates SR latch. S equal to 1, R equal to 1 causes no change in output Q in case of NAND gates based SR latch. So this is just the explanation of what is given in function table. Okay. So this is what is the explanation for SR latch. Okay. So next we shall see to the discussion of edge triggered D flip-flop, which is part of question number 4C only. In question number 4C, they have asked to demonstrate working of SR latch and edge trigger D flip-flop. So SR latch discussion is over. Next we shall move on to edge trigger D flip-flop. Okay. So next, edge trigger D flip-flop. D flip-flop means data flip-flop. So D flip-flop means data flip-flop. Output Q will be same as data input D. If output Q is made to change only at the edge of clock, then that type of D flip-flop is called as edge triggered flip-flop. There are two types in this. First one, master slave D flip-flop. Second one, D type positive edge triggered flip-flop. So first we shall see master slave D flip-flop. So this is the block diagram for master slave D flip-flop. Flip-flop or latch we can call this. So this is one D latch, this is second D latch, this is called as master latch, this is slave latch. So we are discussing master slave D flip-flop or latch. So latch means here flip-flop. This is master flip-flop, this is slave flip-flop. There are two inputs for each. Here it is D and enable. Data or D and enable inputs. The output of first D flip-flop, that is master flip-flop, is connected as data input to second one. So the actual data is given to data input of master flip-flop. Its output, that is intermediate output, that is Y, is given as input to data input of second flip-flop, that is slave flip-flop. So Q is the output of whole assembly here, one master slave flip-flop it is. Enable, that is taking the signal from clock signal. When clock is positive here, because of inverter it will be negative here. So during first half cycle of clock, this data gets lashed into first master flip-flop. It appears at its output Y. So when this is positive, this is negative. So when this is enabled, this is not enabled. During second half clock cycle, so clock becomes negative, but it is inverted. This becomes positive, this is negative, this is not enabled. This is enabled. During first half, what this data has appeared here, that during second half cycle, because that negative cycle becomes positive here, this slave flip-flop is enabled. Hence, this input appears as output here. Hence, after one clock cycle, this D data input, whatever is given, appears as output of whole assembly, that is at Q. That is what is master slave flip-flop. Here Y is the bit stored in master D latch. At negative edge of clock pulse, output Q will be equal to the bit stored in master D latch, that is bit Y. Means during positive edge of the clock cycle, master is enabled, data input D appears as Y output here. During negative clock cycle, because of inverter, second slave flip-flop is enabled, this is not enabled. So that data input which was at Y output appearing as input here, that will be latched and that will appear onto Q output. Hence, in one clock cycle, D appears at Q. Whatever input bit is given, that appears as Q here. Okay, that is regarding master slave D flip-flop. So next, D type positive edge triggered flip-flop. So this is the diagram for D type positive edge triggered flip-flop. Okay. So in D type edge triggered flip-flop, if D is 0, this data input is 0. When clock becomes 1, this clock becomes 1. R changes to 0. This R changes to 0. Then this causes Q to 0. So flip-flop goes to reset state. Okay. So when D is 0, Q is 0 here. Similarly, if D is 1, when clock goes from 0 to 1, this one, S changes to 0. This S changes to 0. This causes the circuit to go to set state, making Q equal to 1. This is how when D is 0, Q is 0, D is 1, Q is 1. That actually what is the function of D flip-flop or data flip-flop. The output is whatever D is. Okay. Any changes in D input while clock 1 doesn't affect the output. So that is what is the working of D type positive edge triggered flip-flop. So that completes the answer for 4C. With this we come to the end of discussion of question number 4ABC, asked for 20 marks. Okay. I hope you understood. Thank you.